Bismillahirrahmanirrahim. Wassalatu wassalamu ala rasulillah. So we will solve a citation problem for chapter 26, which is about resistance and resistors. So here we have our first problem. You have a high voltage copper transmission line that has a diameter of 2 centimeters and a length of 200 kilometers. And it carries a steady current of 1000 amperes. So this is my transmission line, which is very long between, let's say, two cities. So I give you here the radius, which is 1 centimeter. And I give you the length of the transmission line, L, 200 kilometers. And it carries a steady current. So I give you the current is equal to 1000 amperes. Okay, now if copper has a free charge density of, so this is number of electron per meter cube for copper, it's 8.5, 10 to the power 28 electron per meter cube. Okay, this is the number of electron per meter cube, okay, the electron density per meter cube. So over which time interval does one single electron travel the full length? So I want basically, let's say one electron is here. What time it will take to travel the full length? So you know that the time the electron will take will be the length divided by the speed of the electron. Now, what is the speed of the electron? The speed of the electron is actually the drift speed. We call it VD. Okay. So VD is the drift speed. Now I know the length, 200 kilometers. Now I need to get what the drift speed, and then I will plug it here and I get the time. So what are the data of the problem? They gave me the intensity. They gave me, the cross-sectional area by giving me the diameter or the radius. So in reality, I can calculate the what? J, which is the current density. Current density is current I divided by cross-sectional area. Okay, so this is the current density in amperes per meter square. So it's I divided by the cross-sectional area is pi r square. I know I, 1000 amperes. I know r square, so I know what's the current density. Next, you know that the current density actually, we demonstrated this in class, we derived this, is equal to N, which is the number of electron per meter cube, the density of electron, the density of free charge, the density of charge carriers in my material, which is copper here, and it's given here, multiplied by the charge, which is E, okay, of course, multiplied by the V drift. So this formula is in your formula sheet, of course. So that means my V drift is just I divided by the cross-sectional area pi r square. Now, of course, I divide by 1 over NE. So this is my V drift. Okay, so let's calculate the V drift, for instance. So I have 1000 amperes divided by pi r square. R is 1 centimeter. So basically 10 to the power minus 2. You put it in meters, of course, square. So what is N? N is 8.5, 10 to the power 28. But don't forget to multiply by E. Okay. Let me write it down here. I don't have space here, but you multiply by E at the denominator. So E is 1.6, 10 to the power minus 19. You put everything in SI units. So of course, your VD will be in meters per second. So you do the calculation, you get 2.34, 10 to the power minus 4 meters per second. This is a V drift. And this V drift is very small. How much is it? Basically, it's 0.23 millimeters per second. Okay, actually the electron moving in your wire is, the speed is very small. The drift speed, which is the speed that my electron has when I apply an electric field, is very small. Okay, good. Now this is my V drift. Let me just now plug it here. So the time is 200 kilometers, 10 to the power 3 meters, divided by V drift, which is 2.34, 10 to the power minus 4 meters per second. Meters goes away and second goes up. So how much do you get? I think you will get something like 8.5, 10 to the power 8 seconds. So this is the time it will take my electron to go from one end to the other end. And this is how much? This is 27.5 years. Okay. So basically the electrons are moving very slowly in your circuit. Now, how come when I switch on the light, it comes instantaneously? I will send you a nice video about that. Okay. Basically, the flow of energy is different from the flow of charge. But we are in physics 102, so we'll simplify. But in reality, they are, you have a field, you have an electric field, you have a magnetic field, and this electric field and magnetic field are moving almost at speed of light. Okay, that's why when you switch on, it comes automatically. But the drift speed, the speed at which my electrons are moving under an applied electric field is in reality very small. Okay, very, very small compared, for instance, to the random speed. Okay, the random motion speed. And we talked about that in class. Okay, random motion speed is roughly, let's say, 10 to the power 6 meters per second. Okay, the speed is very small. Anyway, let's go to the next problem. So here I give you the drift velocity of free electron in wire, and as you see, it's very small. V drift is 7.84 10 to the power minus 4 meters per second. So if this is the drift velocity for free electron in a copper wire, what is the electric field in the conductor? Again, this drift speed is what? Is the speed at which electrons are moving under electric field. Okay. I wrote an expression for you in class, and I told you that this drift speed can be written as E divided by M multiplied by tau. Basically, this is the acceleration, this is the tau. Tau is the time between collision. So it's due to the electric field, okay? And it's very small. Now here, of course, I will not be using this formula. Okay, I give you V drift. This formula is not in your formula sheet. I just gave it to you for you to see the big picture. Now here I give you V drift. Now I'm asking you what is the electric field that I have applied to my copper wire. So you know something. Here I give you what? I give you N. So it's 8.49 10 to the power 28. Electrons per meter cube. This is the density of free charge in my copper. The number of electrons per meter cube, you see, 10 to the power 28, as before, it's copper. And I give you also the resistivity for copper. Resistivity for copper is 1.70 10 to the power minus 8 ohm meter. Okay, good. And here I'm asking what's the electric field. So I will use Ohm's law. Okay, you look at your formula sheet. In your formula sheet, of course, we demonstrated, we derived this in class. E is equal to resistivity multiplied by current density. We demonstrated this in class. Let's derive it again. You know that Ohm's law for, copper wire, the voltage across my wire is the resistance multiplied by the current. Do you agree with this, right? So that means the voltage. Now, what's the resistance? The resistance, we already showed that it's the resistivity, rho, multiplied by the length of my copper wire divided by the cross-sectional area, multiplied by I. Let me divide by L. So V divided by L. By the way, V divided by L, this is just the electric field. Okay? The voltage across divided by the length of the wire. This is the electric field inside the conductor, inside the wire. So this is rho multiplied by current divided by area, cross-sectional area. You know that current divided by cross-sectional area, this is just my current density. So you see that E is just rho multiplied by current density. And this is the Ohm's law, okay? This is the Ohm's law that you are very familiar with. This is another version of Ohm's law, okay? Electric field is resistivity multiplied by current density. So as I told you, resistivity is a property of the material. Resistance is a property of the object, okay? Resistivity is for copper, for instance. This is the resistivity for copper. But resistance depends on the length, on the geometry, okay? That's why resistance is rho L divided by A, okay? Anyway, let's get our electric field. I know the resistivity. I can know easily what's my current density. What's the current density? Well, we know that current density J is N, which is the number of electrons per meter cube, the density of free electrons multiplied by E multiplied by VD. So the electric field that I'm looking for is rho multiplied by N multiplied by E multiplied by VD. So I put everything in SI units. What is rho? Rho is given 1.7 10 to the power 28 ohm meter multiplied by N and minus 8, sorry, 1.7 10 to the power minus 8. N is 8.49 10 to the power 28. E is 1.6 10 to the power minus 19. And VD is given. Okay, VD is 7.84 10 to the power minus 4. You put everything in SI units, you will get, of course, your electric field in meters, in volt per meters, okay? Because electric field is a voltage divided by a distance. So you will get your electric field and it will be equal to this 0.18 volt per meter or Newton per coulomb, okay? So remember the formulas, and of course, in your formula sheet, and know what's the physics going on. Now let's go to the next problem here. So I have a nichrome. This is basically an alloy made of nickel and chromium. Okay, I think it's 80%, 20%. I give you the length and I give you the cross-sectional area. Okay. So in reality, I'm giving you what? You will see. Okay. So when connected to a potential difference of 6 volt, a current of 1 amperes is going through the wire at room temperature 20 degrees Celsius. Find the resistivity rho of the wire. So first, you see here, I give you the potential difference and the current. So I'm giving you the resistance, which is V divided by I. So which is 6 volt divided by 1 amp. This is 6 ohm. This is the resistance of my wire. And of course, this resistance is equal to resistivity multiplied by the length divided by the area. So now I know the resistance, 6 ohm. I know the length, 2 meters, as you can see here. Of course, you put everything in meters. You know the area, 2 millimeters square. You put it in meters square, of course, and you go for it, and you get your rho is 6 10 to the power minus 6 ohm meter. Okay. Now let me show you something very quickly. So that's how you get the resistivity. So as you see, these are different materials, and the resistivity at room temperature, 20 degrees Celsius. The conductivity is just the inverse of the resistivity. Okay. And then here I have the temperature constant. I will come back to this just in a second. So you see, silver has the highest conductivity, and then copper. etc., etc. But of course, silver is more expensive than copper, so we will use copper for our daily, let's say, wires in our lab, at home, and etc., etc. Now, where is the material that we are looking at? You see, it's here. Okay. It's here, 1.1. This is 10 to the power minus 6. This is my resistivity, and this is my conductivity. Okay, good. Now, let me go back here and share with you the rest. So actually, the temperature coefficient of nichrome, the temperature coefficient of resistivity is this number, okay, per degree Celsius. If the wire temperature is decreasing by 40 degrees Celsius, will the resistance increase, decrease, or remain the same? As we demonstrated in class, rho at any temperature, so in reality, the resistance and the resistivity depend on temperature, okay? Sometimes the dependence on temperature can be negligible for our daily life use. So we can say that the resistance is fixed, okay? And then we have what we call an ohmic resistor. An ohmic resistor is when this ratio V divided by I is constant, okay? But for a non-ohmic resistor, where the resistance and the resistivity are temperature dependent, we know that rho is equal to rho naught 1 plus alpha T minus T naught. Alpha being the coefficient, temperature coefficient of resistivity. Okay. Of course, if this delta T is negative, of course, my resistivity will decrease. Okay. So here, if I multiply by L divided by area, I can have the same equation for resistance. And this, you saw this in the lab. Okay, resistance at any temperature is R naught, resistance at my reference temperature, multiplied by 1 plus alpha T minus T naught. Okay, alpha is a constant, and that's called the temperature coefficient of resistivity. And yet, of course, it's a number divided by Kelvin or Kelvin degree or Celsius degree, okay, which is the difference of temperature. Okay, because it's a difference of temperature, it doesn't matter if it's in, that delta T in Kelvin is delta T in degrees Celsius. So of course, if delta T is negative, the resistance will decrease, okay? Good. Now let's look at this problem here, which is also straightforward. So if you double the cross-sectional area of a wire and keep it connected to the same battery, what's the change in power? So I have a wire and I have a certain cross-sectional area and a certain length made of a certain material, okay? And I connect it to what? A battery, which has a certain voltage V. Of course, the battery is an EMF, so V is constant. Of course, here the length is constant. Now the cross-sectional area is what I'm doubling. So what's the change in power? As you know, power across any device is a current multiplied by V. But here, of course, here you have a wire. So V is RI. Okay. So V is RI, so I will have I square multiplied by R. Okay, this is the power across a resistance. Okay. I can also write it as V square over R. Good. So here I'll be using V square over R because I know that V is constant. So power dissipated by my resistor, by my wire, is V square over R. But you remember, R is rho L divided by A. Okay, so if I double the area, the cross-sectional area, I'm dividing the resistance by 2. Do you agree with that? So if A becomes 2A, the resistance will become half of the initial resistance. That means the power will double, okay? Because it will be half at the denominator, so that means the power will double, okay? So in this type of problem, always you write your final equation, and from there you can do your analysis, okay? Good. Of course, here, this is what I will be using because this V is fixed. If I gave you the current, you will be reasoning using the current, I square R, if you want, okay? Depending on the data of the problem, you reason with what you get, what is constant, and you vary the rest. So here, of course, I'll be using this formula. Next problem, if you double the resistance of the wire and keep it connected to the same battery, okay, so V is constant, what is the change in the drift velocity? Okay, great. So what do we need to do? First, we need to look at the resistance. Resistance is equal to rho, resistivity, and the resistivity is kept constant, multiplied by L divided by A. Okay. So if I double the resistance, that means now my R is multiplied by 2. Okay. Now, how I did it, I did not tell you. I did not tell you, did I multiply by 2 the length, or did I divide by 2 the cross-sectional area? I did not say anything. Just I'm telling you that I doubled the resistance. Okay, so we just keep that, we keep it as it is, and we say that the resistance has been doubled. Now, how the drift velocity will change? Now, let's get the drift velocity. As you know, drift velocity, I can get it from the current density. Current density is NEV. Okay, good. N being the charge density. E is the absolute value of the charge, okay, 1.6 10 to the power minus 19, and V is a V drift. But you know that the current density is just current divided by area. So basically, V drift will be equal to what? Current divided by area, which is the current density, divided by NE. Do we agree with this? Okay, great. So, but what is current? Current is just, V divided by R, because it's a wire. So I have V divided by the resistance, divided by the area, divided by NE. Okay, this is a V drift. Do we agree? So here, V is constant. A, I consider it as constant. NE, of course, is constant. So here I'm just doubling what? The resistance. So if I double the resistance, of course, the resistance is at the denominator. I'm dividing VD by 2. Okay. So the drift velocity will be half. Will be divided by 2. Okay. Good. And this type of problem will come again and again and again. You write your expressions, and then you consider everything is fixed, you know, depending on the data of the problem. Here I'm fixing the voltage. So I better write VD as function of the voltage of the battery, okay? And I see that the resistance is at the denominator. If I double it, I will half the VD. Good. Now let's solve this problem here, which is very important. So what do we have? The question is, what is the required resistance of a heater? Okay. So a heater is just a resistor, because you know that a resistor, when it's carrying a current, it will heat up. Okay, it will become a heater because it's dissipating thermal energy. So what is the required resistance of a heater? Basically, what's R? That increases the temperature of 1.5 kilogram of water from 10 to 50 degrees Celsius in 10 minutes while operating at 110 volt. I give you the specific heat of water, okay, which is this. So it's a heater. What the quantity of heat absorbed by water? Of course, it will be mass water multiplied by the specific heat of water multiplied by final temperature of water minus initial temperature of water. And I can calculate this. I know the mass of water. I know the specific heat of water. I know the final temperature, 50 degrees Celsius. I know the initial temperature. Okay, good. Now, of course, what's the power? So this is heat or energy absorbed. Now, of course, the power absorbed by the water is just Q water divided by delta T. This is the power absorbed. Basically, the energy per unit time, okay? The rate of energy transfer, okay? So this is it. And I get this power, okay? It's M water, C water, T final minus T initial divided by delta T. And delta T here is 10 minutes, basically 10 times 60 seconds. And this is the power. Now this power, of course, is given by the heater. So this power is the power of my resistor, dissipated by the resistor. And what's the power dissipated by the resistor? You know, free formula for power dissipated by a resistor is IV, which is the same I as I square R, because V is RI, okay? You just plug it here, you have I square R, but it's also as V square over R. Why? Because I is just V divided by R. So I can plug it here, okay? And I have V square over R. So here I'll be using V square over R because I gave you V already. Okay, so the question now, I know V square, of course. Now what's R? Of course, R is just equal to what? Basically V square times delta T divided by mass water, C water, T final 50 minus T initial, which is 10. Okay, so you have 110 square delta T, which is 600 seconds, divided by mass water 1.5, C water is 4190 SI units. You put everything in SI units. Of course, this is delta T, you put it in, you leave it as it is, because delta T in Kelvin is the same as delta T is in Celsius, so 40. And this gives you a resistance of 28.9 ohm, okay? So this should be the required resistance of my heater, okay? And you have used this, by the way, in the lab. You remember when we were doing, you know, calorimetry experiments, we were using a heater and we use this formula, okay? Good. Next question, same problem. I have an electric device which heats water by immersing a resistant wire in water. So it generates 300 or 3000 joule of heat per minute. So I'm giving you the power. The power is 300 joule, the time is minute. Power is energy divided by time. 3000 joule divided by 1 minute, 60 seconds. So I have a power of 50 watts. Okay, when an electric potential difference, this is the voltage, is 12 placed across it. What's the resistance of the heater wire? Of course, this power is just equal to V square over R. Of course, I know everything here. My only unknown will be R. V square is 12 square, so I get my R. Of course, it will be V square divided by power, and you get this. Okay, this is a typical type of problem, very simple. Okay, now let's solve this problem here. So we have a wire, and I give you the cross-sectional area of the wire. I did not give you the length. Okay, so I have a wire, and I give you the cross-sectional area. So this is it. So this is a wire, and it dissipates because it's a wire. So it's so I give you the power, which is the rate of energy transfer, the rate of, you know, thermal energy dissipation, basically. Okay, how much energy is dissipated per unit time? So it's 154 watt. Of course, what is in joule per second? Energy divided by time. So this is the power, the electric power, okay? And this is equal to what? The power of a resistor. So it's IV, or V square over R, or I square R. So for a heater or resistor, I have these three formulas. Now here, what did I give you? I said you that, it dissipates this power when connected to 32 volts. So this is a V, and I gave it to you. What is the current flowing in the wire? I'm asking you current. Of course, I'll be using this. Okay, so I give you this V. I'm asking you what is the current. The current will be the power divided by the voltage. Okay, so it will give you 154 divided by the voltage. What is the voltage? 32. I believe you will get 4.8 amp. Okay, good. If I gave you, for instance, if I ask you what is a resistor, what is a resistance? Okay, you can get the resistance, right? Okay, you can get it using this formula here. Okay. Good. Second question. A copper cable is to be designed to carry a 6 ampere current. I gave you the current. I is equal to 6 amp. Okay, good. Now with a power loss of 12 milliwatt per meter. So here I'm giving you a power loss. I'm giving you power dissipated per unit length. Per unit length. And this is 12 milliwatt, 10 to the power minus 3, milli is 10 to the power minus 3 per meter. Okay, good. Now, I want to design this cable. So the question is, what is the required radius of the copper wire? I give you the resistivity of copper, raw copper. Okay, 1.7, 10 to the power minus 8 per meter. Good. Okay, now how should I do? Well, you know that power for a wire, power for a wire is equal to what? I can use IV. I can use I square R, so that's what I will use, is equal to I square R. And this is equal to I square, the current square, and I gave you already the current, multiplied by R. Now what is R? R, the resistance, is resistivity length divided by cross-sectional area. So it's the resistivity rho multiplied by length divided by the cross-sectional area. Okay, good. So let me divide by L. So I will have power divided by L. So now I have power dissipated per unit length is just I square, current square, multiplied by resistivity rho divided by cross-sectional area. Okay, so I know this power per unit length. Okay, it's 12 milliwatt per meter. I know the resistivity rho, I know the current I. Now what's the cross-sectional area? Is just pi r squared, because it will be cylindrical, right? So that's what I want, okay? So power per unit length is I square rho divided by pi r squared. So I want the R. So R will be equal to what? It will be square root of I square rho divided by pi. And here, of course, I will have P divided by L. Okay, good. So I know everything here. So it will be square root of 6 square rho. I know rho. You plug it here, you know pi. You know P divided by L is just 12 10 to the power minus 3. And I believe you will get the radius which will be required is roughly 4 × 10⁻³ meters, basically 4 millimeters. Do the calculation, okay? So you know everything, you just get me what's the radius. Okay, let's go to the next problem here. So we have a cylindrical rod, and I give you the length of the cylindrical rod. So this is L, 1.5 meters, and I give you the radius. Oh, sorry. 1.5 meter cylindrical rod of length. Okay, this is the length L. Okay. Let me remove this. So I gave you the length L of the cylindrical rod is 2 meters, and I gave you the radius, you put it in meters, of course, 0.25 10⁻²meters. So it's connected to a power supply that maintains a constant potential difference of 18 volts across its end. So I know that delta V across my wire is 18 volts, whatever happens. Great. So at 20 degrees Celsius, the current through the wire is this. Let me write that down. At 20 degrees Celsius, current at 20 degrees is 18.5 amp. At 95 degrees Celsius, the current I95 is 17.5 amp. Okay. Now the question is, how much power will be dissipated in the rod if it is heated to 200 degrees Celsius? So I want power at 200 degrees Celsius. Here I'm saying ignore any thermal expansion of the rod and take the reference temperature to be 20 degrees Celsius. So T0 will be T20, basically 20 degrees Celsius. Okay. Good. So here I'm ignoring any thermal expansion because you know that if I heat up, of course, my rod will expand, thermal expansion, but I will neglect that. Here I will just focus on the coefficient resistivity, temperature coefficient of resistivity, not on the coefficient of thermal expansion. Okay, I just consider that, you know, the thermal expansion is negligible. I ignore it. I will just focus on the effect on temperature, on the conduction, or on the resistivity. Okay, great. Now let's solve this problem. As you know, the resistivity rho depends on the temperature and is equal to rho naught 1 plus alpha T minus T naught. Okay, that means that my resistance at any temperature, and of course here I'm considering a non-ohmic resistor. Okay, so I have a non-negligible dependence of my resistance on temperature. Okay? So this is a non-ohmic resistor. Okay, so the temperature, the resistance is temperature dependent. If I had an ohmic resistor, it will be constant. So I don't look at the temperature dependence of my resistance. So here I have RT, which is R naught, my resistance at my reference temperature, factor 1 plus alpha T minus T naught. Great. Okay, so what do we need to do? Let's calculate here. You see here, my delta V is always fixed. So let's calculate R20, which is here, which will be my R naught, by the way, because I take 20 as my reference temperature. So it will be delta V divided by the current at 20, okay? Because resistance is V divided by the current I. So my resistance at 20 degrees Celsius is delta V divided by this. So it will be what? 18. Well, that's my delta V divided by I, which is 18.5. And this is in ohm. This is my reference resistance. Okay. Now, what's my resistance at 95? My resistance at 95 will be also delta V divided by the current at 95. So it will be 18 divided by, what's my current at 95? 17.5 ohm. Okay. Of course, you see, when I increase my temperature, I increase my resistance. So that means I will decrease my current. That's why this current is smaller than this current. Anyway, now I know that, this is my resistance at 95 degrees Celsius, but by definition using this is just equal to R20, 1 plus alpha T, which is 95, minus 20. Okay, good. And so this will give me what? This will give me alpha. So I will have 18 divided by 17.5 ohm. This is equal to R20, which is 18 divided by 18.5. Okay, 18 goes away. 1 plus alpha times 95 minus 25 minus 20 is equal to 75. So my alpha, I can calculate it. So what is alpha? If you do the calculation, you will find your alpha. So alpha, I find like 7.619 10 to the power minus 4. Okay. And of course, alpha, the unit of alpha, minus 1. Okay. Okay. It's degrees Celsius minus 1. Or, over degrees Celsius, let's say. Okay, now I get my alpha. Now let's go back to our problem. The problem is I want to find P at 20. What's the power dissipated at 200 degrees Celsius? Well, you know that the power dissipated by a resistor at 200 degrees Celsius will be V square. By the way, V square, I know it is 18 square. It's fixed, okay? You see, that's what I said here, remain constant, because it's N, divided by R square. But which R should I use? I should use, of course, R of 200 degrees Celsius. Not square, of course, V square. Power is V square divided by R. Okay, so V square, 18 square divided by R, but the R is at 200 degrees Celsius. So basically it will give you 18 square divided by, what's the R at 200 degrees Celsius? It will be R naught, which is 18 divided by 18.5. 1 plus alpha. Now I know what alpha is, right? Alpha is here. I just replace by alpha. Now it will be, of course, 200 minus 20. Okay, so I know everything here. Okay, I know alpha. I plug it here. 200 minus 20 is 180. And you calculate your power dissipated at 200 degrees Celsius. Okay, so if you do that, you get a power which is dissipated, which is 293 watt. Okay, great. So it's a non-ohmic resistor. Again, I ignore all the thermal expansion of the rod because all this happen with, it will expand. If I heat up, the rod will, but I neglect it, I ignore it. Next, I have a cylindrical resistor and I give you the radius. So the radius is given 2.5 10 to the power minus 3 meters. Okay, you put it in meters, of course. I give you the length. For the length, 4 centimeters, which is 4 10 to the power minus 2 meters. So it's made of a material which has this resistivity, and I give you rho, 3.5 10 to the power minus 5 ohm meter. And the question is, what is the potential difference when the energy dissipation rate is 1 watt? Again, power is 1 watt. Power is the rate at which energy is transferred, okay? Basically, it's energy divided by time, or energy divided by dt. Anyway, for a resistor, we know what the power is. The power is IV, or I square R, or V square over R, okay? So which one should I use here? What do you think? So I want the V. Okay, this is what I want. So I better use this. So power, which is 1 watt, will be equal to V square over R. But you remember R is rho L divided by A. Okay, so I will have V square over rho L, I know L, A is pi R squared. Okay, so I know the power. I know rho, I know L, I know R. I put everything in SI unit. My only unknown will be V. Okay, and that will give me the potential difference when the energy dissipation rate, which is the power, is 1 watt. Okay, and it will give me 0.27 volt. Let's solve this problem now. So read it very carefully. We have a uniform cylindrical copper wire that has to be manufactured out of 1 gram of copper. So mass is 1 gram of copper. If the wire is to have a resistance of half ohm, so resistance should be half ohm, what will be the length of the wire? Okay. The question is, what is L? Knowing resistance, of course, you know that L is rho, resistance R is rho L divided by cross-sectional area. Okay, so here I give you the density, mass density of copper, 8,940 kilogram per meter cube, and I give you rho copper. Okay, so how to solve this? So we start by the resistance, R, which should be half ohm, is equal to rho. I know rho copper, by the way, it's given. By the way, this rho here is electric resistivity. Okay, remember, electric resistivity, it's in ohm meter. Okay, and remember as well, electric conductivity, sigma, which is just 1 over electric resistivity. So you remember Ohm's law, V is Ri. I can also write it as E is rho J. Okay. By the way, here I can put vectors if I want, because electric field is a vector, J is a vector, and they are pointing in the same direction. As the coefficient between them is rho. Okay. So this can give me J is 1 over rho E. So basically J is just sigma E. And this is also Ohm's law. Okay. Sometimes in a problem, I'll give you J, and I'll give you electric field, and I ask you what the electric conductivity sigma. Okay, this is electric conductivity. Conductivity. Okay. And you know the units, it's inverse of unit of this. Anyway, that was a side note. Now let me come back to my problem here. So the resistance is rho L divided by A. I know rho, I know R. Now what should be L divided by A? Good question. So here what I gave you is the mass, and I give you the density of copper. So you know that, of course, density of copper is just mass of copper divided by volume of copper. But here I want it to be uniform, cylindrical, uniform. So this is a uniform. So this should be my cross-sectional area. Of course, it's pi r square, and this is the length. So the volume is just cross-sectional area multiplied by the length L. Let me call it length capital L. Okay. Great. So I have density of copper is just mass of copper divided by cross-sectional area multiplied by length, which is the volume. Okay. Now that means that my cross-sectional area is just mass divided by density of copper multiplied by length. So now let me take this and just plug it here. So I'll have resistance is rho. Now L. Now I will divide by A, which is M divided by D multiplied by L. So I have my resistance, which is rho L square D divided by M. Okay, so I know R, resistance, I know rho, I know D, which is the density of copper. So I call it D just, to avoid confusion between mass density and electric resistivity. And this is a mass of 1 gram, of course, we put it in kilogram. So this gives me what? My L will be just square root of mass multiplied by resistance divided by what? Rho density of copper. Let me put the numbers. Mass is 1 gram, so 10 to the power minus 3 kilogram. What's the resistance? I put everything in SI units. Resistance is half ohm. What's the density? I mean, what's the electric conductivity? Electrical conductivity 1.7, 10 to the power minus 8. What's the mass density? 8.94, 10 to the power 3. And when you do this, you will find a length of 1.81 meters, which is, of course, the first answer. Okay, great. Let's go to the next problem. And I gave you the solution, have a look at it. And by the way, as I said, sometimes in some solutions, there are some typos. This forces you to have a critical thinking, okay? So for instance, here, a small minor typo is the square root was forgotten. But it's written here. Okay? So use your critical thinking. Don't just watch the solution, but do it and use your critical thinking and find the solution. Great. Okay, let's look at this problem here. So we have a copper wire, and I give you the cross-sectional area and the length, okay, and the current. And it's uniformly distributed across the area. How much electric energy is transferred into thermal energy in 1 hour? Okay, we already discussed this. So power is energy divided by time. So I need energy. So the energy will be power times the time. So what is power? What is power dissipated by a wire? I have different formulas. Power is IV, which is IR squared for my wire, for my heater, or V squared over R. So here I will use what? Better use IR squared, of course, right? So the energies that I dissipate will be not IR squared, it's I square R. Careful, okay? I square R. Okay. So I square R. Why? Because you know that V is RI. So you just plug it here, so you get I square R. So I square R multiplied by T. So I know I square. What's I square? So 2 square. Now what's R? Well, R is rho L divided by A. I know rho of copper, it's given here. I know L. I know cross-sectional area. So I know everything. Okay, and then I know the time. What's time? 1 hour. So I put it in SI units. So 1 hour is seconds. So that's it. I have 4 times rho, which is 1.69, 10 to the power minus 8. SI units, L, 4, cross-sectional area, 2, 10 to the power minus 6. And then I multiply by the time, which is this. Of course, it will give me in SI units, so it's in joule. I will get 487 joule. Okay, this is it. This is what we did here. And alas. Okay, this is also straightforward. We have a continuous beam of electron, and I give you the current. Okay, it's 0.125 amp. Is incident on a target. How many electrons strike the target in a period of 23 seconds? You know that electron is charge divided by time. That means my total number of charge will be current multiplied by time. So my total number of charge that will strike the target is 0.1 0.25 times 23 seconds. And I would get it in Coulomb. Okay, you calculate this, and this gives you the number of charge in Coulomb, total number of charge. Now, how many electrons? You know that charge is quantized, so this is number of electrons multiplied by E. So number of electrons will be just IT divided by 1.6, 10 to the power minus 19 Coulomb. Okay, IT is 0.125, 23. And this gives you how much? 1.8, 10 to the power 19. Okay, very straightforward. And yeah, you get 1.8, 10 to the power 19. Now let's look at this problem here. The resistance of a wire at 0 degrees Celsius is 79. Okay, so I'm giving you resistance. R0 is 70, not 79. Okay, 70 ohm. Okay. If the temperature is increased to 100 degrees Celsius, the resistance increases by 50%. So resistance at 100 degrees Celsius is 50, it increases by 50%. So it will be R0, do you agree with me? Plus 50% of R0. Okay, this is an increase of 50%. Okay. So that means that my resistance at 100 degrees Celsius is just 1.5 R0. Okay, this is an increase of 50%. Now the question is very simple. Find the resistance at 120 degrees. Just using these two information here. So you know that here I don't have an ohmic resistor. I have a non-ohmic resistor. The resistance depends on the temperature. Okay, so I can use that resistance at any temperature is R0, 1 plus alpha, alpha being the temperature coefficient of resistivity, T minus T0. Okay, so R100 will be R0, R at 0 degrees Celsius, 1 plus alpha, T minus T0, and it's 100 minus 0. So here I can get what's alpha. Okay, I can simplify by R0 and I get what's alpha. So alpha will be what? 1.5 minus 1 divided by 100. Okay. So this gives you what? 5 10 to the power minus 3 per degree Celsius or Kelvin. So this is my alpha. Now, what is my R at 120? It will be R0. Let me write it down. R0. 1 plus alpha that I already know. 120 minus 0. So it will be 70. 1 plus alpha, 5 10 to the power minus 3, multiplied by 120. And this will give you 112 ohm. Okay? Good. The more, the higher temperature I have, of course, the resistance will increase. The temperature increase, this delta T is increasing, is positive. So of course my resistance will increase. Of course, resistance increasing for the same voltage, that means that my current is decreasing. Okay. Okay. That's it for today. Please solve all the rest of the problem. I have put all the exams. So just practice, 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 practice. Okay. Thank you very much. Assalamu alaikum wa rahmatullah.